Thanks for joining us for Phosphorus Science Now. I'm your host, Matt Schultz with the Sustainable Phosphorus Alliance. We speak of legacy phosphorus as that which has accumulated in watersheds and water bodies, sometimes over long periods of time. This includes phosphorus in both dissolved and particulate forms that builds up in the sediments of rivers and streams. Legacy phosphorus in such sediments can bleed into the water column over time, thereby delivering nutrients that feed blooms of harmful algae and bacteria. Today's guest asks how long these contributions last and how they change along the length of a river or stream. Dr. Kevin Wallington of ETH Zurich University in Switzerland used a modified version of a well-known hydrological model called SWAT to explore what would happen to these legacy contributions if we reduced phosphorus loading from a particular wastewater utility in Illinois. Hey, Kevin, thanks for joining us for Phosphorus Science Now. I'd love to hear some more about your paper. If you could let me know about your collaborators and who your funders were for this project.
Yeah, thanks for inviting me. I'm excited to share this work of myself and my collaborators, Shiming Kai and Margaret Kalchich. This was part of an NSF Infuse project, Innovations at the Nexus of Food, Energy, and Water Systems, looking at phosphorus recovery and agricultural conservation practices and their impacts on connected food, energy, water systems. And the backdrop for our project for this work is the really stubborn problem of high nutrient loads in rivers, which contribute to water quality problems such as the Gulf of Mexico hypoxic zone, also known as the dead zone for its impact on marine life. And in particular, the nutrient we investigated is phosphorus. And as I mentioned, high phosphorus loads in rivers have been a stubborn problem. One key reason for its difficulty is that phosphorus can have very long residence times in watersheds due to its tendency to adhere to soil and sediment particles. And so even after a phosphorus source has been remediated, so-called legacy phosphorus that entered the watershed years ago can be remobilized and impede future water quality progress. And this figure shows one estimate for these residence times of phosphorus. And we homed in on the in-channel or in-stream component of legacy phosphorus. And you see here the estimate that these in-stream phosphorus legacies last less than 1 year. But this estimate is actually very uncertain, or really it's somewhat incomplete. And it's incomplete because prior studies haven't fully considered the role of spatial scale. Spatial scale is really important, especially for in-stream legacies, because phosphorus moves downstream in a sort of stop and start fashion. And the residence time can be very different when considering a small part of the stream network versus a larger part. And this concept in of itself is not new, but nonetheless, estimates for phosphorus legacies at large spatial scales have been really rare or abstract. And that's because it's really difficult to directly observe the downstream cascade of phosphorus legacies. And until now, there hadn't been computer models that could simulate this phenomenon for large areas or long times. And so that's why in a previous study, we developed an extension to the soil and water assessment tool to simulate in-stream phosphorus retention and remobilization in large watersheds. And then having this model, we now have a tool to better answer the question driving this research: for how long will in-stream legacies delay reaching water quality targets at locations far downstream from remediation? And so for our investigation, we used the Upper Sangamon River in central Illinois as a case study. The Upper Sangamon watershed is mostly agricultural, but there is a large point source phosphorus discharger, the Sanitary District of Decatur, located at the star on the map. But the sanitary district is also preparing to remove over 90% of the phosphorus from its discharge in order to meet new forthcoming regulations from the Illinois EPA. And so we used our extended model to evaluate how in-stream phosphorus legacies would cascade downstream after the remediation of this point source. And to isolate the impacts of in-stream legacies from other phosphorus sources, we designed 3 counterfactual modeling experiments. These experiments each span 40 years, split evenly between a historical period and a future period. And so first, in the status quo scenario, the point source discharged the amount of phosphorus as was measured from 2001 to 2020 for the historical period, and then continued this high discharge during the 20-year future period. In the baseline scenario, the point source discharges only 10% of what was observed in the historical period, and then continues this low discharge in the future period. And then finally, in the legacy scenario, the point source discharges the full amount during the historical period, but then switches to only 10% during the future period. So beginning on the first day of the future period, the only difference between the legacy and the baseline scenarios is the amount of legacy phosphorus that is built up within the river during the historical period. And we can attribute any load differences during the future period to this in-stream legacy phosphorus. And so we evaluate these load differences between these scenarios at the 4 checkpoints that we have downstream from our point source to illustrate downstream cascade of water quality recovery. And here's what we see during the first 200 days after the point source reduction. Plotted here are phosphorus loads at the watershed outlet, so the last checkpoint, for the 3 modeling scenarios. And we want to give special attention here to the width of the dark blue band in the plot, which is the contribution of in-stream legacies to phosphorus loads at the outlet. And for reference, at the top of the screen now is the stream flow on these days. And so we can see that during the first 50-ish days, while flow is low, there's a small but consistent contribution of legacy phosphorus. This is due to diffusion of dissolved phosphorus from the stream bed into the water column. And during these days, legacy phosphorus contributes nearly the entire phosphorus load in the river. But the diffusion of dissolved phosphorus is pretty short-lived and winds down after about 50 days. However, when high flow events occur between days 100 to 150, in-stream legacies contribute very large amounts to the phosphorus load, up to several thousand kilograms in a single day. You can see the thick blue band there. On these high flow days, the strong flow flushes streambed sediment downstream, and phosphorus that is adhered to the sediment is mobilized with it. And this mechanism of legacy phosphorus remobilization by sediment erosion persists much longer, as we'll see in the coming slides.
And Kevin, can you explain for a moment what the difference is between diffusion and erosion exactly? So what's going on chemically?
Yeah, so diffusion is when you have dissolved phosphorus both in the water column and in the stream bed. And depending where the concentration is higher, the flow of dissolved phosphorus will move from the higher concentration to the lower concentration. So if it's higher in the stream bed, then you'll see a flow of dissolved phosphorus from the stream bed into the water column. This dissolved phosphorus can attach, adhere, adsorb really is what it's called, to the surface of a soil particle, in which case that phosphorus can then be mobilized if the particle itself either erodes into the water column, is resuspended into the water column, and then it could be redeposited further downstream if that sediment settles back into the stream bed.
Got it. So the difference is really the adsorption.
Mm-hmm. Yeah.
Great. Thanks.
Yeah. And so looking at longer time periods, the first thing we're going to show here is the concentration of phosphorus in the stream bed between these different checkpoints of the river. And the legacy scenario here is shown in dark, and then the baseline scenario is shown in light. And so noting the different scales on the vertical axes here, you see that during the historical period for the legacy scenario, the section of stream bed between the point source and the first checkpoint, which is the top plot, accumulates phosphorus up to a concentration of about 1,200 milligrams of phosphorus per kilogram of sediment. And in contrast, in the bottom plot, the section of stream bed between the third and the final checkpoint only reaches about 300 milligrams per kilogram, so much lower. After remediation happens in the legacy scenario, which begins at the dashed vertical line at year 21 here, the streambed phosphorus concentration in the upstream section, that's the top plot, recovers to the same as the baseline level in about 2 to 3 years. And then in contrast, in the downstream section at the bottom plot, the stream bed phosphorus concentration in the legacy scenario takes about 10 to 12 years to recover down to the baseline level. And so we see that further downstream from the remediated point source, legacy phosphorus remains in the stream bed for a longer time. And in the same vein, we see that legacy contributions to the river phosphorus loads are much greater and persist much longer for checkpoints that are further downstream. This plot here shows the cumulative contribution of in-stream legacies to river phosphorus loads at each checkpoint. And the first takeaway is that we see the total magnitudes after 20 years at these checkpoints are vastly different. For instance, at the first checkpoint, that's pink, the in-stream legacies contribute 50,000 kilograms of phosphorus over the 20 years, while at the final, most downstream checkpoint, in-stream legacies contribute 400,000 kilograms of phosphorus. And then the second takeaway is we see that the first checkpoint, virtually all in-stream legacy contributions occur within the first 2 to 3 years after the point source reduction. And then in contrast, for the final, most downstream checkpoint, although most legacy contributions do occur during the first 3 years, there's still meaningful large contributions for about 9 years. So to emphasize this spatial aspect that we're interested in, this is a plot of the years until in-stream legacy phosphorus is, quote, exhausted versus the distance downstream from the remediated point source. To approximate the date at which we're saying in-stream legacies are exhausted, we're using the date at which 95% of all future load contributions, which is what was plotted in the prior slide, when 95% of those contributions have been made. And so we have the 4 model checkpoints from our simulation here. And then just to emphasize the general nature of the relationship, we've included 2 rough potential trend lines. And this plot really drives home the point that distance downstream is essential information for any estimates of how long in-stream legacies persist. And this is an important finding for management of nutrient loads in the Mississippi River Basin and of hypoxia in the Gulf of Mexico, because the distance from the sanitary district point source to our watershed outlet is approximately 70 kilometers. And the distance from the point source to the Gulf of Mexico is 2,600 kilometers. And so you can see extrapolation of this trend here suggests that in-stream legacies from this point source, if you look at these trend lines, could contribute to phosphorus loads at the Gulf of Mexico for 17 to 36 years. And that estimate, though, should be treated with a grain of salt, since the stream conditions within our watershed can be quite different from those along the rest of the journey to the Gulf. But nonetheless, if the goals of the Gulf of Mexico hypoxia task force are to be met, upstream states and watersheds will have to reach load reduction targets years or maybe even decades in advance of the task force's target dates. So to conclude, using our extended watershed model and long-term counterfactual simulations, we arrive at an answer to our motivating question. And we can say that cascading in-stream phosphorus legacies can delay water quality recovery for several years, not just 1 year, for locations far downstream from the remediated source. And these results that we've shown demonstrate this conclusion in the form of elevated streambed phosphorus concentrations at locations further downstream, in the form of higher in-stream legacy contributions to river phosphorus loads further downstream, and longer lasting legacy contributions to loads at locations further downstream. So thank you. And please read the paper for more details.
Yeah, great. Thanks, Kevin. That's a nice presentation. 2 questions for you. One, so we're essentially living in the legacy scenario, right? Where Decatur is going to do this removal from their plant.
Yes, that's right.
These are model data. And so is there any opportunity to measure whether the predictions are actually lining up from the model, are actually lining up with the phosphorus concentrations at the various checkpoints that you've queried?
So in our particular watershed, there's probably not a monitoring campaign that would be sufficient to validate the findings in our watershed. There are some pretty robust sampling campaigns that have started in recent years, but they're pretty recent because it's very resource intensive to actually observe something like this, because you'd have to measure phosphorus concentrations and flow to get phosphorus loads very frequently to catch these short-lived high load events. You'd have to measure at multiple locations so you could see, multiple checkpoints along a river. And you'd have to also, you'd have to have measured remediation so you know how much, decreased source you have happening. And then even if you were able to do all of that and have measured differences in your loads and have a good estimate of that at all of your different locations, there's still a difficult problem of then attributing your loads to different sources and saying what of your measured load is coming from, for instance, an in-stream legacy, like we're talking about here, versus some other sort of source.
Sure.
And so it's a role that models help to fill, where you can do these sort of counterfactual experiments. And so really it's kind of a work that, you have to have models and monitoring really working together. And there's on both ends a lot of kind of room for advancement and growth.
Right. So people should send you a lot more money, right?
Yeah. Me
Yeah.
and a lot of other people.
Yeah. Yeah, the last thing is, you mentioned about state nutrient reduction strategies and how they probably need to better account for this internal loading. Are they listening to that message? And what can they do about it other than reduce their expectations for improvement? So what's sort of best management practice, I guess?
Yeah, that's really hard to say. A lot of management practices and focus on load reductions right now are either focused on decreasing what would be called edge of field phosphorus losses from agricultural fields. So fertilizer that's applied in a field that runs off and makes its way to a stream, or reductions of a point source phosphorus source, like what we are talking about in this study. But there's starting to be some more discussion of interventions within a stream itself that could potentially maybe not remove, but at least offset some of the impacts of in-stream legacy phosphorus. And so that's something that potentially could be researched or invested in more. And then at a high level of the management, there's a need for recognition of these time delays and just when targets are set for the states versus the Gulf. A lot of states, at least a handful of the states that are kind of members of the Gulf of Mexico Hypoxia Task Force, have goals in terms of percent reductions and target dates that exactly match the reduction target dates for the Gulf itself. And so those seem, in light of this study, to be unrealistic, because a state could reach its reduction and then it could still take several years for the impact of that reduction to make its way all the way down to the Gulf. And so there's a need for, some just reevaluation of targets, whether that means becoming more aggressive on the state end or accommodating longer times that are going to be needed to reach goals at the Gulf.
Great. Yeah, thanks for that. And if people are interested in this topic, we did a Phosphorus Science Now a few months ago with Andrew Margonaut on stream bank erosion, and there's some great info in there too that I would direct people towards. Kevin, thanks so much for taking the time to join us for Phosphorus Science Now.
Thank you so much, Matt.